Hi guys, this is AS Chemistry, Organic Chemistry, and we are looking at organic synthesis. Question 10. Organic reactions involve substances which may be atoms, molecules, ions, or free radicals. We also apply the terms electrophilic, nucleophilic, addition, elimination, and substitution to organic reactions. Consider the following reactions. Using the terms mentioned above, state as clearly as you can the nature of each of the following reactions. Reaction 1. Now, reaction 1 is a reaction between methane and chlorine to produce chloromethane and HCl. So, this is an example of a free radical substitution reaction. Reaction 2 is an alcohol being converted into an alkene with the removal of water. This is an example of a dehydration reaction, but dehydration is not a term given in the choices above. So, water is removed from the alcohol. So, we can say that water has been eliminated. So, this is an example of an elimination reaction. Reaction 3 is CH3I reacting with OH negative ions, producing an alcohol and I negative. So this is nucleophilic substitution. And CH3COCH3, which is a ketone reacting with HCN to produce a cyanohydrin, is an example of a nucleophilic addition reaction. So these two are not ours, but we know what they are. The third reaction is nucleophilic substitution, and the fourth reaction is nucleophilic addition. By considering the four reactions above, suggest a formula for each of the following substances. In each case, state which reaction you are considering. So, one substance that is an addition product, something that has been added. So, we have in reaction 4, we have a CN atom that has been added. We also have a hydrogen that is added to oxygen to produce OH. So the addition product is CN. One substance that is a leaving group. So in reaction 3, which is nucleophilic substitution, the I negative ion has been replaced by OH negative. So I negative ion is the leaving group. One substance that behaves as an electrophile. Electrophile means electron deficient species towards which the lone pair of electrons are attracted to. So one substance that behaves as an electrophile. So CH3I has the CH3 positive ion acting as the electrophile. So in reaction 3, we've got CH3I, out of which the CH3 will act as the electrophile because the OH will be attracted towards it, and the lone pair of electrons of the OH will be attracted to the positive charge on the carbon atom in CH3I. And this can also be possible in reaction 4 because in reaction 4, we've got the CH3 C double bond O single bond CH3, the Cn negative ion, the lone pair of electrons on carbon, will be attracted towards the positive charge on the carbonyl carbon atom because it is bonded to the oxygen atom, which is more electronegative. So there are two possibilities of a substance behaving as an electrophile. What is meant by the term nucleophile? A species having a lone pair of electrons which are attracted towards an electron deficient species called an electrophile or a carbocation. So it need not have a negative charge on it, but presence of a lone pair of electrons is a must. Reactions 3 and 4 involve nucleophiles. For each reaction, give the formula of the nucleophile. So reaction 3 is nucleophilic substitution. So the nucleophile here would be the OH negative ion, and reaction 4 is nucleophilic addition. So the electrophile here would be the CN negative ion. One characteristic reaction of ethene is its ability to decolorize bromine. In the reaction, ethene behaves as a nucleophile. Suggest an explanation of how ethene can behave in this way. So we have a double bond. A double bond consists of a sigma and a pi bond. A pi bond has electrons present above and below the plane of the two nuclei of the two carbon atoms. So there are electrons above and below the double bond that are present. So uh, ethene can behave as a nucleophile because of the presence of the pi bond, which is rich in electrons. They are present above and below the plane of the two nuclei of carbon. So, since electrons are present above and below the plane of the nuclei of the two carbon atoms, the double bond is rich in electrons. So, because of the double bond and the pi bond of the double bond to be very specific, ethene can behave as a nucleophile. Question 11. Organic chemistry is the chemistry of carbon compounds. Type of organic reaction that you have studied are listed below. Addition, elimination, hydrolysis, oxidation, reduction, substitution. Addition and substitution reactions are further described as follows: electrophilic, nucleophilic, and free radical. Complete the table below. Fill in the central column by using only the types of reaction given in the list above. Use both lists when appropriate. In the right hand column, give the formulae of the reagents you would use to carry out the reactions given. So here is the complete table along with the available options to use. So the first organic reaction is the conversion of a bromoalkane into an amine. So the type of reaction here is replacement of Br negative with NH2. So this is an example of a nucleophilic substitution reaction. And the reagents used are ammonia. Ammonia will be the reagent used. They have not asked for conditions. So ammonia and in ethanol, because we heat it under pressure, that is a condition that is not required, but ammonia is present in ethanol. So these are the reagents that would be required. The next reaction is an alcohol converting into a bromo alcohol. That means nothing happens to the alcohol group. In fact, the CHC group is converted into CH2Br, which is an example of a free radical substitution reaction. And the reagents used are Br2, and Br2 should not be aqueous, it should be liquid or vapor. It cannot be aqueous Br2. So Br2 liquid is used and UV light is required, which would be the conditions for this reaction. The next organic reaction is a ketone being converted into a cyanohydrin. So this is an example of a nucleophilic addition reaction, and the reagents for this reaction are HCN along with NaCN and HCl to provide acidic conditions and also to provide the H positive ion if required. So these are the reagents for nucleophilic addition of a ketone. The last organic reaction is an alcohol being converted into an alkene. So this is an example of a dehydration reaction, but dehydration is not an option given in the list above. A dehydration reaction results in the elimination of a water molecule from an alcohol. So the type of reaction that would be mentioned here would be an elimination reaction. And the reagents for this would be H3PO4 and SiO2. These are the reagents. The conditions are 70 atmospheres and 300 degrees Celsius, but the conditions are not asked over here. These are the conditions for the hydration of alkenes. So this is wrong. These are not the conditions for the dehydration of an alcohol. These are the conditions for the hydration of an alkene to form an alcohol. So let's revisit the reagents and correct them. So we are supposed to remove the OH group and the H group. So this requires two possible catalysts. Either it could be Al2O3, which would be present at 350 degrees Celsius, or we can have concentrated H2SO4 present at 170 to 180 degrees Celsius. So these are the conditions for the removal of steam from an alcohol to produce an alkene. Question 12. Compound X has the molecular formula of C4H8O2. Treatment of X with sodium metal produces a colorless flammable gas. With sodium metal. Sodium metal would result in the production of hydrogen gas. Okay, so this gas is hydrogen. What does this result tell you about the functional group that could be present in X? So the functional group present in X could either be a carboxylic acid or an alcohol group, because the OH group present in carboxylic acid or the OH group present in alcohol would react with the sodium metal, and a displacement reaction will occur in which the sodium metal will displace the hydrogen atom from the OH group, releasing hydrogen gas. So it is possible with carboxylic acid and alcohol. There is no reaction when X is treated with sodium hydrogen carbonate. That means carboxylic group is not present. What does this result tell you about the functional group that could be present in X? So carboxylic acid group is not present, which means alcohol group is present in compound X. When X is shaken with aqueous bromine, the orange color disappears. What does this result tell you about the functional groups that could be present in X? Disappearing of the color of bromine indicates the presence of a double bond. That means an alkene functional group is present, the molecule of X has the following features. The carbon chain is unbranched and the molecule is not cyclic. So it is a straight chain compound. No oxygen atom is attached to any carbon atom which is involved in pi bonding. So the double bond present will not have an oxygen atom attached to it. No carbon atom has more than one oxygen atom joined to it. So a carbon atom will only have a single oxygen atom joined to it. There are five possible isomers of X which fit these data. Four of these isomers exist as two pairs of stereoisomers. Draw the displayed formula of each of these two pairs. So let's put this together. C4H8O2. So we've got four carbon atoms, one, two, three, and four. So the carbon chain is unbranched. No oxygen atom is attached to any carbon with a double bond. So if we place a double bond in between, that means the oxygen atoms are placed on the terminal carbon atoms. And since it is not a carboxylic acid and an alcohol group, we can complete that as the alcohol group. So what is left? So two hydrogen have been used up, six hydrogens remain, one hydrogen each on the two carbon atoms with the double bond, and four hydrogen atoms on the terminal carbon atoms. So this is the structure of one of the possible isomers of X. So draw the displayed formula of each of these two pairs. So pairs of stereoisomers. So a double bond would have a cis and a transform. So we would have a C double bond C with hydrogen on the same side and CH2OH on the other side of the two carbon atoms with a double bond between them. So this would be the cis isomer of the compound. And as for the trans isomer, we would have the carbon atoms with the double bond, the hydrogen atoms on opposite side of the double bonded carbon atoms with the CH2OH group present on opposite sides of the carbon atoms with the double bond as well. So this is the trans isomer of this compound. So this is the first pair of isomer and they said it is another pair. So we will need to make another structure with this molecular formula. So now, since the double bond is present in between, we could have cis trans. So what if the double bond is present at a terminal carbon atom? So that would be C double bonded C. So this would give H and H. Then we would have an H here. Then we could have a C and a CH3 here. So no, it cannot be a CH3. So it has to be a CH3 CH2OH because no carbon atom can be bonded by two oxygen atoms. So what remains is a hydrogen on one side of the carbon atom that remains and an OH group on the other, converting this carbon atom into a chiral carbon atom. So now we would have a pair of optical isomers. So the optical isomers would be carbon with hydrogen on one end, OH on the other, CH2OH on the third position and CH double bonded to CH2 on the fourth position. And its mirror image would have the CH2OH and the CH2 groups switched, while the H and OH remain where they are. So on this optical isomer, the CH2OH is placed on the left carbon atom and the CH double bonded to CH2 will be placed on the right carbon atom, forming a pair of optical isomers. These four isomers of X show two types of stereoisomerism. State which type of isomerism each pair shows. So pair 1 shows this trans or geometric isomerism, and pair 2 shows optical isomerism. Question 13. The molecular formula C4H8O can represent a number of compounds which have different functional groups and which show different types of isomerism. Compounds H, J, and K each have the molecular formula C4H8O. In each of the molecules of H, J, and K, the carbon chain is unbranched and the molecule is not cyclic. No oxygen atom is attached to any carbon atom which is involved in pi bonding. So if a double bond is present, it will not be bonded to an oxygen atom. When compound H is reacted with sodium metal, a colorless flammable gas is produced. So hydrogen is released. So this shows presence of either a carboxylic acid or an alcohol or both. Both J and K give an orange red precipitate when reacted with 2,4-dinitrophenyl hydrazine reagent, but only K reacts with Fehling solution. So K is an aldehyde and J is a ketone. Suggest possible structural formulae for H, J, and K. Three structural formulae are possible for H, but only one for J and one for K. So the structure of K is an aldehyde. So a four carbon aldehyde would be CH3, CH2, CH2, and CHO. So the molecular formula will be C4H34567 8 and O. So this is correct. J is supposed to be a ketone. So CH3, CH2, C double bond O, single bond CH3. So C4H8O. This is also correct. And H is supposed to be either an alcohol or a carboxylic acid. And looking at the question more closely, it cannot be a carboxylic acid because the question mentioned that no oxygen atom is bonded to a carbon atom with a pi bond on it. So, carboxylic acid has the C double bond O group in which there is a pi bond between a carbon and an oxygen atom, which means that it cannot be a carboxylic acid. That means it is an alcohol. So, an alcohol with a C4H8 combination of carbon and hydrogen atoms, meaning a double bond is also present. So we can start off with a compound with a CH2 double bonded to CH. Then we have a CH2, and then we can have a CH2OH group. Counting the number of carbon, hydrogen, and oxygen, we have got C4H 2, 4, 6, and 8, and O. So this is correct. Now we need three different isomers of this compound. So we can have an isomer with the double bond changing position from the first carbon atom to between the second and the third carbon atom. So it would be CH3, CH, double bonded to CH, single bonded to CH2, OH, which would also be having a molecular formula of C4H34567 8 and O, which is correct. Or we can have the first structure drawn again, but the OH group changing its position from the terminal carbon atom to the carbon atom adjacent to it on the left. So it would become CH2 double bonded to CH, single bonded to CH, then OH on this carbon atom, and then single bonded to CH3. So here in total, we've got four carbon atoms. In total, we've got 2, 3, 4, 5, and 6, 7, 8 carbon atoms and one oxygen atom, making this structure correct as well. And the OH cannot be placed on the two carbon atoms with a double bond on them because the question said that the carbon atom with a pi bond on it will not be bonded to an oxygen atom. So these are the three possible structural isomers of compound H. In addition to being structural isomers of each other, some of the possible structures for H, J, or K show cis-trans isomerism or are chiral. Draw the displayed formula of those isomers which show cis-trans isomerism. And the next part asks, draw the displayed formula of those isomers which are chiral, indicating in each case the chiral carbon atom with an asterisk. So we need to revisit the structures of H, J, and K. So just by looking at these structures, structures K and J will neither have a cis-trans isomer nor a optical isomer present. So we're left with H and the three structural isomers of H. So the first one will not have any chiral carbon atom or will not show cis-trans isomerism because the first carbon atom has two hydrogen attached to it, which negates the requirements of geometric isomerism. In the second compound, we have a double bond on which we've got two hydrogen atoms. So they can be on the same side in a cis isomer and on the opposite side in a trans isomer. So this one will show cis trans isomerism. Whereas if we look at the last structural isomer of H, we've got a chiral carbon atom present where the OH group is attached because on one side we've got a hydrogen, on the other a CH3, on the third side an OH, and on the fourth side we've got a CH and a double bonded CH2 group present, which are four different groups attached to the same carbon atom, making it a chiral carbon atom. So now to draw the geometric isomers and the optical isomers of these two compounds. So for the cis-trans isomer, we have two carbon atoms with a hydrogen on both of them. On one, we've got CH2OH present, and on the other, we've got a CH3 group present. So this is the cis isomer of that compound. Now to draw the trans isomer. So the trans isomer would be C double bonded C, a hydrogen on one side of the double bond and a hydrogen on the other side. The CH2OH group carried over on one side of the double bond and the CH3 group remains on the same side of the double bond. This is the trans isomer of the same compound. Next, we have to draw the optical isomer. So in order to draw the optical isomer, we need to have a mirror in the center. Then we will have carbon atoms with four bonding positions in which the bonding position above and below would have the same groups present on them, whereas the bonding positions on the left and the right as shown in the 3D diagram will have the groups switching their positions. So on one of the optical isomers, we will place a hydrogen atom on one side, the OH group on the opposite side of hydrogen. Then we would have CH double bonded CH2. If placed on the right of the first optical isomer, it will be placed on the left of the second optical isomer. And then we are left with a CH3 group. So on the first isomer, the CH3 group is placed on the left, and on the second isomer, the CH3 group is placed on the right, resulting in the formation of two optical isomers having a chiral center or a chiral carbon atom marked with an asterisk.